Hello everyone, myself Om Mehta here and welcome. Today we are going to talk about something that's been sitting inside every computer, every CPU, every phone, every laptop, on the server, on the planet. That is your CPU's pipeline. You've probably seen that number 2 gigahertz, 3 gigahertz, 4 gigahertz, 5 gigahertz and assumed it means your processor is doing billions of things every second. And in a way it does. But the real story is something different of how it achieves that speed is much more interesting and a little deceptive as well. So this video is about pipelining, the technique that lets CPU pretend to be faster than they really are, and the hazards that break that illusion. So now let's start with a simple question. If your CPU runs at 3 gigahertz, does it execute 3 billion instructions per second? Naively, you might say yes, 3 billion ticks per second, one instruction per tick, that's 3 billion instructions. But executing a single instruction is not a single step. It involves fetching an instruction from the memory, decoding what it means, performing the actual computation, possibly reading or writing memory, and finally writing the result back. That's 5 distinct steps. If each step takes one clock cycle, then one instruction takes 5 cycles. At 3 GHz, you're getting 600 million instructions per second, not 3 billion. So, how do modern CPUs close that gap? The answer is pipelining. Before we understand pipelining, we need to understand what those 5 stages actually do. So, first, instruction fetch, or IF. The CPU reads the next instruction from memory using a register called the program counter. Think of it as a CPU's reading finger pointing to the next line. Now, second is the instruction decode, or ID. The CPU figures out what the instruction means, what operation to perform, and which registers are involved. It reads the source values from the register file here. Third is the execute, or EX. This is where the actual work happens. The arithmetic logic unit, ALU. The ALU performs the addition, subtraction, and comparison. For memory instructions, it compares the addresses and computes them. And then the branch condition gets evaluated. Fourth is the memory access, or MEM. So for load and store instructions, the CPU reads and writes data from the memory here. For arithmetic instructions, this stage just passes the result through. Fifth is the write back, or WB. The result is written back into the destination register. After this stage, the instruction is officially done. So this is the five-stage pipeline. So here is a key insight about those 5 stages. Those 5 stages don't have to run one at a time. Think of a car assembly line, which uh, let's say while one car is getting its engine fitted, the next car is getting its doors, and then third car is getting being painted. So different cars, different stages, all at the same time getting done. So a CPU pipeline works exactly the same way. While instruction 1 is in execution stage, instruction 2 can be in the decoded stage, and instruction 3 is being in a fetch stage. Every stage is busy every clock cycle. Look at the timing diagram on the screen. Without pipelining, 3 instructions take 15 cycles, 5 each. Now, with pipelining, the same 3 instruction just takes 7 cycles. That's a 53% reduction. That's almost twice as fast. The general formula is cycles is equals to pipeline depth plus the number of instructions minus 1. So the pipeline fills up over the first few cycles, then delivers one instruction per cycle at full speed. This is how our CPU earns its gigahertz rating, not by doing one thing super fast, but by doing many things simultaneously in perfectly overlapping stages. Now, here is the lie begins. But here the CPU starts where the CPU's whole story starts to fall apart. Pipelining assumes that every instruction is completely independent of every other instruction. In real programs, that's almost never true. Now, There are three categories of situation called hazards that force the pipeline to pause, insert bubbles, or throw away work it's already done. Data hazards occur when an instruction needs a result that hasn't been computed yet. Structural hazards happen when two instructions need the same hardware resource at the same time. And control hazards arise when a branch instruction forces the CPU to guess which code to execute next. Each of these hazards is a crack in the illusion. Let's look at each one. First is the data hazard. Read after write. That's RAW. Now, the most common hazard is the read after write dependency or RAW. This happens when instruction 2 needs to read a register that instruction 1 is still writing. Look at the code example. Here, the add instruction writes its results into the register R1. The very next instruction, that is subtract, needs to read R1, but in the pipeline, add doesn't write R1 until its write back stage, which is clock cycle 5. That is here. Subtraction needs to read R1 during its ID stage, which is clock cycle 3. That's 2 cycles too early. The value isn't ready yet. Without any solution, the hardware detects this conflict and inserts two stall stages right here. Now, essentially, empty bubbles in the pipeline. The pipeline freezes those later stages while earlier stages keep running. You can see those stall cells on the timing diagram, gray dashed, doing nothing in the process. This is the CPU lying to you. You see your 3 GHz chip and assume it's always busy. But right here, 2 out of 8 cycles are completely wasted on a simple 2 instruction sequence. Now, the fix, data forwarding. That's also called as bypassing. Hardware designers were not happy with those stall cycles. Their solution is called data forwarding, sometimes also called as bypassing. The core idea is very simple. Why wait for the result to be written back to the register file when we can grab it directly where it's sitting inside the pipeline itself? At the end, uh, at the execution stage, the result is sitting in the pipeline register with an extra wire called as a forwarding path. We can route the result to the input of the next execute stage. No waiting for the write back, no stop. The timing diagram shows this in action. Here, we can route that result directly to the input of the next execute stage. Instruction 2 gets its value from the execute or memory forwarding path, delivered exactly when it's needed. Zero stall cycles here. However, there's one case of forwarding which we can't fix. The load use hazard. A load instruction gets its data from memory, and the memory data only arrives after the memory stage. Uh, but the next instruction needs it at the start of the execution. There's simply no way to go back in time. One stall cycle is unavoidable here, but compilers can often reorder instructions to hide it. Forwarding eliminates roughly 50% of the data hazard stalls in typical programs. It's one of the most important microarchitecture trick ever invented. Now let's look at the structural hazards. Structural hazards are conceptually the simplest. They occur when two instructions need to use the same piece of hardware at the same time at the same clock cycle. Now, the classic textbook example is a processor with a single unified memory instruction fetch. The if stage reads from memory to get the next instruction. At the same time, a load instruction in the memory stage is also trying to read from the memory. One memory, two simultaneous requests, which creates a conflict. Now, the solution, use separate memories, or more accurately, separate caches, a dedicated instruction cache and a dedicated data cache. This is called Harvard architecture as opposed to the unified von Neumann architecture. Modern processors always use this at the L1 cache level. Another example is a single floating point unit. If two FP instructions are back to back and both need the CPU at the same cycle at the same time, one must wait. The fix is to pipeline this FP The third and arguably most fascinating type of hazard is the control hazard caused by the branch instructions. When your code hits an if else statement or a loop, the CPU encounters a branch instruction like BEQ, that is branch if equal. To know where to jump next, the CPU has to evaluate the branch condition, and that evaluation happens in the execution stage, that is clock cycle 3. But by clock cycle 3, the CPU has already fetched two more instructions from the sequential path, hoping the branch wasn't taken. If the branch is taken, those two fetched instructions are wrong. They have to be flushed, completely discarded, and the two cycles are wasted. The naive solution is called predict not taken. Just always assume that the branches aren't taken yet. Branches won't jump. You'll be right sometimes, you'll be wrong sometimes. Modern CPUs are far more sophisticated. They use branch predictors, dedicated hardware units that study the history of every branch and predict its next outcome. The stage predictor used in modern Intel and AMD processors achieve 95 to 99% accuracy when prediction is wrong. On this prediction penalty, the CPU flushes the pipeline, discards the speculative work, and restarts from the corrected address. With deep pipelines of 20 plus stages, a misprediction can waste 15 to 20 cycles. That's why branch prediction accuracy matters so much for performance. Now, let's look at the interactive pipeline simulator. Okay. Now let's make this concrete with an interactive simulator built into this presentation right now. I'll take no hazards. Just a second. I'll take no hazards. First, watch every stage is busy, every clock cycle, one instruction completes per cycle after the pipeline fills. This is the ideal world your CPU advertises to you, which everyone thinks that yes, this is the CPU what you actually think. But now, as I click on raw data hazard, look at the stall cells appearing for instruction 2. Two completely empty cycles. That's real time lost. Now, with forwarding, the same code but the stall disappears entirely. The execution forwarding path delivers right on time. The forwarding is so critical. Finally, the control result. The branch results at EX. Two instructions already get fetched. Guessed. Notice how the target instruction can only begin in cycle after the flush. Every expedition in your real program looks like this. The key takeaway from this demo: the pipeline is not a guarantee. It's an optimistic assumption. Hard hazards are the CPUs admitting reality is more complicated than the brochure suggested. Now let's see the real impact. So how do we measure the real cost of these hazards in practice? The key metric is CPI, that is cycles per instruction. An ideal pipeline has CPI of exactly 1.0, but real programs have CPI between 1.2 to 1.8 thanks to stalls. The formula is simple. CPI is equals to 1 plus average number of stalls per cycle instruction. The inverse is IPC, instructions per cycle. Modern superscalar processors can issue 4 to 6 instructions simultaneously, multiple pipelines running in parallel, but hazards still drag the effective IPC below that peak. The most powerful weapon against hazards is out-of-order execution, or OOO we can say. Instead of executing instructions in strict program order, the CPU dynamically reorders them to keep pipelines busy. If instruction 5 doesn't depend on instruction 3 or 4, execute 5 first. Modern processors can have 512 instructions in flight simultaneously using an algorithm called Thomas Solo's algorithm, which is originally from 1967. Software also helps loop unrolling, compile instruction scheduling, and cache-friendly memory access patterns all reduce the number of stalls the hardware needs to handle. when pipeline breaks security. So here's where the story takes a darker turn. In January 2018, researchers disclosed two catastrophic vulnerabilities called Spectre and Meltdown. Both exploited the exact techniques we have been discussing: speculative execution and pipelining. Here is how Spectre works. A branch predictor guesses the outcome of a conditional branch and speculatively executes code beyond it. During the speculation, the CPU loads the data into cache, potentially from the protected memory that the program shouldn't be able to access. When the speculation is wrong, the CPU rolls back to its register state. It discards the bad instructions, but the cache is not rolled back. The data is still sitting there in the cache. An attacker can measure how long memory accesses take. Cache hits are fast, misses are slow. By carefully crafting requests and measuring timing, they can reconstruct the secret data that was speculatively loaded, even across processes boundaries, across virtual machines, between kernel and user space. Patches to fix Spectre and Meltdown disabled parts of speculative execution. Performance dropped from around 5 to 30% on server workloads. The CPU optimization trick had a real world cost when the abstraction was broken. Now, the summary and the key takeaways from this video. Let's bring everything together. So, pipelining is the reason modern CPUs can approach their advertised clock speeds by overlapping 5 stages: fetch, decode, execute, memory, and write back. The CPU completes one instruction per cycle at full throughput. Data hazards, especially read after write, that is raw dependencies, are the most common disruption. Forwarding eliminates most of them, but load hazard always costs one cycle. Structural hazards are shared hardware are solving by duplicating the resources, separating the instructions and data caches, pipelining the functional units. Control hazards from branches are managed through highly accurate branch prediction, achieving 95 to 99% accuracy in modern processes. Uh, and the deeper lesson that your CPU's gigahertz rating is a theoretical maximum and not a guarantee. So the real performance measured in IPC is always lower, shaped by the constant battle against the hazards. The lie isn't dishonest, it's aspirational, and the engineering that goes into approaching that aspiration, the forwarding paths, branch predictor, of the water engines, is some of the most brilliant work in the history of